This is the LFET demo, which stands for Low Frequency Electromagnetic Technique. This system is used for the scanning of OD tubes or pipes. Basically what this is a 8-channel system for this demonstration. We have 8 channels, which is in the center of this scanner right here. And they're labeled 1 through 8. And we can put 6, 16, 32, or even 64 channels depending on how big the tube or pipe is. For this demonstration, we have what's here, which is a tube out of a water wall in a utility plant. And before I scan it, if you look inside, you're going to see up top, if you look up at the top here, I'll hold that right up to the camera here. Like so, you're going to see there's all kinds of indications up top, and that's the area I'm going to scan for you. Now, we're going to go into our Windows software system. Just a couple things to keep in mind. We designed to make our own equipment, all software. We're going to go to F2, which is our TS2000 software, which is used for scanning on the outside of tubes. Come up to the option. You have the option for the row, the tube, and the run. And the run is for like if you want to do a repo on something. Obviously the row and tube are self-explanatory. The option for the C drive, so you can name the drive whatever you want and hit OK. I'm going to overwrite that file, but this also gives you plan information. So you can put the name, the location, the unit number. Now we're going to come up to our screen. Now if you look at our screen, I mentioned earlier that we have 8 channels to go across. We also have 8 individual screens. Each screen represents a channel which is in our scanner. A couple other things you want to keep in mind. When we're putting our scanner on, this is a 2-man system. One man is running the scanner along the length of the tube. The other person is watching the screen. So what we're doing is we're putting the scanner on the tube. We're going to gain it. Usually we're going to run about 10 hertz for carbon steel material. Now if it's non-ferrous, usually we're going to be up probably in 1,000, anywhere from 1,000 to 1,500 hertz. Obviously the thicker the tube, the lower the frequency. So what you want to do is you want to get a good baseline. You're going to notice where that red line goes across. We have our signal which rides right across it. This tells us that we have good base metal. Now what we're looking for is any rise in our signal. So when we hit the space bar, we start scanning along the length of the tube. You'll notice we're getting rises in our signal. These are all indications that there's a change in tube material. Notice I didn't say wall loss, and there's a reason for that. It's also what's called hydrogen damage. Now a lot of times hydrogen damage, you'll get a rise in signal like this. Now you go to UT that, it's going to show almost near wall, like full wall. So say if this is 250, it may show like 240 or 248. But what you're looking at the back wall reflection, and if there isn't any, that shows you that there's what's called hydrogen damage in the tube. Now this one typically has corrosion, so there's going to be wall loss associated. So if you put a UT meter in, some of these indications here are going to show you that there's almost over 50% wall loss in the tubes. But you notice each channel is affected differently. The first couple channels and the last channel show very little as far as the signal goes as far as wall loss. But once you get in the middle channels, you're going to notice how big the signal is. That's because in the middle of the tube is where most of the wall loss is. Now if I hit our F4 key, this is going to give you your 3D views. There's top views, there's side views, there's a raw phase, and there's a process phase. And these are all 3D views, which enhances the image. Now if I hit F4 again, it's going to pull all 8 channels of these together. I can lower my scale a little bit so you can see it better. But what you're seeing is you're seeing the indications of the tube. So if I turn this tube sideways and you look at this signal right here, it gives you a representation of all 8 channels scanning along the length of this tube. Also keep in mind that, you know, when you're doing UT, you're only doing spot checks. You might do a spot here, spot here, spot here, but you're missing everything that's in between those tubes. So it's very important that we're doing a continuous scan throughout the length of this tube. Another thing to keep important too, there's a lot of other companies out there that have a system somewhat similar to this, but one of the most important things you got to keep in mind about this system here is the tube cleanliness. Tube cleanliness, typically all we need is a water blasting, and that's for like your coal-fired boilers, just to knock off some of the loose scale. But because what we want a smooth surface, because we have wheels that scan along the length of the tubes. Most other systems out there from other companies, you have to do a sandblasting. So and sandblasting can be very expensive, whereas opposed to water blasting, it's a lot cheaper. Also, our coverage. A lot of systems out there just actually scan, and they're just looking at what they call the crown section of the tube. So they're just maybe looking at maybe 30 degrees of the tube. With our system, we're getting close to 160 degrees of the tube. Now, you notice there's a little bit off to the side here that we're not actually getting. But we're getting probably about 160 degrees of the tube on it. So that's another very important factor. But looking at our signal, we have our phase and amplitude. And by looking at our phase, we can give an approximation of what the diameter is. By looking at our amplitude, that's going to give us the volume, or in other words, like, you know, how deep the flow is. Now, before we come out on site, we want to make sure that we have the proper calibration. So if the tube's like a 3-inch 250, what we'll do is when the machine flaws in maybe 20, 40, 60%, that way when we come out on site, we can make a calibration. We can size any flaws that we find. When we're out on a job, we find a flaw. What we'll do is we'll go over it a couple times to make sure we find the flaw. And then what we'll do is we'll mark it in chalk. So if we have an area, we'll mark it with chalk, go back, rescan it again, make sure we're on the right spot, and then we'll also do UT on it just so we have confirmation. So actually you're getting 2 readings with every flaw we find. And that's why we say approximately we can get 2,500 linear feet in like a 12-hour shift. And that's all dependent on what type of scaffolding. If it's hard scaffolding, we can usually get a little more than when you're on swing scaffolding. And also the number of flaws found. If we're finding a lot of flaws, obviously we're going to have to go back, do some retesting, do some UT for verification. So it takes a little longer. So that's why we say approximately 2,500. And when I say approximately 2,500, 2,500 is like the mean. It could be closer to 2,000 if we're finding a lot of flaws. And if we're not finding anything, it's going to be closer to 3,000 linear feet. Now, if I hit no here, I can go back, and I'm going to flip this tube around just to show you what it would be like if there was a clean tube with the same type of material, same type of wall thickness. You're going to notice my signal straight. Let me get back to the original screen that I had. You're going to notice the 4 or the 8 channels again. I'm going to scan this. Scan along the length of the tube. Now you're going to notice you're not going to see any sharp rises. Now there is a little bit, very minimal. There might be like a little bit of wear, and it just might be because of the way I scanned this demonstration. But you're going to see there's no large indications like it was on the other side. That's showing that there is a good tube. Again, approximately 2,500 linear feet. Keep in mind we also have different types of scanners. We design, make our own scanners, software. And the great thing about that, and one of the advantages we have over other companies, by designing and making our own equipment, we bring backup equipment. So if we have a problem with one of our systems, we always have a backup. And for like reheat tubes, there's probably 4 sensors in here that we can scan in between tubes. So if you have a scanner here, you can put it underneath that. And if there's another tube, this is for tight spaces. That's good for checking for oxygen pitting. We have bend scanners. Another thing, I was telling you about different types of material. This is for ferrous material running approximately 10 hertz. We can also do with stainless steel. You know, if you look in here, there's actually a small pit. It's kind of hard to see, but it's right there. By adjusting our frequency, We can scan over this tube and also pick up indications. All we got to do is adjust our frequency. This is probably about 1500 hertz. Same orientation, scanning along the length of the tubes. And that's basically it for the Lfet. It's short and quick, but it's one of our easier systems. And that's it.